you very much for your kind introduction. And the title of my talk today is Niobium-based photocatalyst for water splitting reaction. Our target reaction is very simple. We like to split pure water into hydrogen and oxygen using solar energy on heterogeneous photocatalyst. Of course, the motivation is as follows. If hydrogen is produced from solar energy and pure water, it can be clean and sustainable energy carrier as well as chemical resource. However, from the viewpoint of the technology, the situation seems to be more serious because we need to produce solar fuels on a large scale at a low cost in the near future. At first, let me get started from the titanium-based photocatalyst. Sorry, it is not a niobium-based one. But as you know, that strontium titanate is a white-colored powder. So these materials can absorb only UV light, so that these materials can absorb only a small portion of sunlight. However, the band gap position of these materials is suitable to split water into hydrogen and oxygen. So this material is actually a so-called UV light responsive photocatalyst. And then we prepare the so-called photocatalyst sheet using these photocatalytic materials and nano-sized silicon materials on a glass plate, just spray coating, then drying up at about 80 degrees C in air. Here we have a 500 milliliter beaker just filled with distilled water. Then if we put this beaker outside under sunlight or just irradiate by a solar simulator, we can get this kind of bubbles coming out. This is the bubbles of hydrogen and oxygen exactly in 2:1 ratio, which is decomposed by using ultraviolet UV light included in sunlight. Then we constructed, based on this type of photocatalytic materials, 100 square meter prototype water splitting system at the Kakioka Research Facility, that is within the University of Tokyo. And as you see, as you see here, there is a small hills, and on top of this hill, there exists a little bit flat place. And here we extended our water splitting panel as shown here. Actually, this is a 3 square meter modules, and then we constructed 33 modules, and here we have 1 square meter additional panel. So total light receiving area is 100 square meter. In addition to that, here we have a gas separation unit. Actually, this work was supported by NIDO funding agency of METI. And this is the first example of the pilot scale solar hydrogen production system using using photocatalyst. And this is an example of the evolving hydrogen and oxygen gases before introducing into the gas separation unit. In this particular case, about 3.6 to 3.7 liter per minute of hydrogen and oxygen gases are evolving. Okay, at first I discussed about the strontium titanate, but as I said, this material absorbs only UV light. Then here I show the tantalum-based photocatalyst as shown here. These materials absorbs very well that invisible light region photons. However, if we look at the niobium-containing photocatalyst, as you see here, these materials absorbs almost all parts of the visible light region photon. So that the niobium-based materials are one of our ultimate target as photocatalysts. And then let me just discuss a little bit about niobium-based photocatalysts, in this case, barium niobium oxysulfide materials. And you don't need to follow the detail of this complicated feature, but we use a niobium pentoxide, then mixed with barium carbonate, then we prepare the barium niobium oxide, then we nitride using ammonia to produce the barium niobium nitride as shown here. And then we further modify this barium niobium oxynitride by modifying cobalt oxide. In this particular case, we use this material as O2 evolution photocatalyst. And then we also modify this barium niobium oxynitride using platinum. In this case, we use these materials as a hydrogen evolution photocatalyst. And here I show that X-ray pattern, and after washing by removing the impurity phase, we can prepare the single phase of barium niobium oxynitride. And as you see here, absorption edge, this is absorption edge, is located at about 740 nanometer. It is very long wavelengths. And here I show the SEM image of these materials. This is the barium niobium oxide materials, precursor materials. Then after nitridation, we obtain this kind of barium niobium oxide nitride. But at this stage, this material still contains some impurity phase. So we remove that impurity phase by aqua regia and then washed out. We obtain this kind of porous barium niobium oxide nitride materials. Then this is XRD pattern when we change the barium to niobium ratio. And but in all cases, as you see, that XRD pattern shows always barium niobium oxide nitride and barium tantalum. This is barium niobium oxide nitride. Then when we increase the barium content, then this XRD patterns peak full width at half maximum becomes narrower. That means that with the increase of barium content, then the crystallinity is improved. However, when we examine the activity of hydrogen evolution, as you see here, when we move from 1.25 ratio to 1.50, we obtain the optimum activity, but further increase of the barium is decreased the activity like this one. So that the barium to niobium ratio 1.5 is optimum ratio. And also we examine the activity of these materials. And I just like to emphasize that apparent quantum yield of this O2 evolution photocatalyst is at this stage about 0.4%. It is not really so high. Then we also examine the hydrogen evolution activity. In this case, that we modify with platinum, but the activity was very low because this is about 1 micromoles. So that's we have, but in any case, this barium niobium oxide nitride was able to produce both hydrogen and oxygen. That means that the band gap of this material is suitable for overall water splitting reaction under visible light irradiation. So that we decided to move to different niobium-based materials. In this case, we prepared lanthanum niobium oxide nitride prepared from lanthanum potassium sodium niobium oxide materials. The reason to use this precursor materials is that the cation arrangement is very similar to our lanthanum niobium oxide nitride as shown here. And this is the precursor oxide materials. And after nitridation, as you see here, these are the atomic scale resolution of TEM image, and they are very well crystallized. Then we examine that the activity and absorption spectrum of these materials. And normally we usually use this lanthanum niobium oxide as a precursor, but in that case, as you see here, baseline absorption is very high. But when we use this lanthanum potassium sodium niobium oxide, after 2-hour nitridation, the baseline absorption is much lower. And then when we compare the O2 evolution activity, comparing to this conventional type materials, starting materials, that hydrogen, oxygen evolution activity becomes much better, and the apparent quantum yield was improved to about 0.85%. Then we further modified our preparation procedure. In this case, we used lanthanum sodium zinc niobium oxide as a precursor materials. That means that this is the precursor materials SEM image. Then we carried as a nitridation. As you see here, we obtain this kind of rather porous lanthanum niobium oxide nitride. And this is more high resolution STEM images. As you see here, the surface region is actually a porous lanthanum niobium oxide nitride, but inside of this material is still remains. That's this oxide materials. However, when we examine the O2 evolution activity, that this is the previous data, and this is this data, and as you see here, the apparent quantum yield was improved to about 1.7%, more than 2 times larger, higher than the previous one. Then we saw that we now decided to challenge the overall water splitting reaction. In this case, we actually doped magnesium into lanthanum niobium oxide nitride. And as you see here, when we increase the magnesium content, this X value, from 0 to 0.1, 0.2, then when we increase to up to 0.33, the baseline is becomes much lower as shown here. And here I show that the band gap energy measurement and also band gap positions for these materials. And as you see, this increase of magnesium doping from X equals 0 to X equals 0.5, the band gap energy is increased like this one. Then we examined these materials' activity for overall water splitting reaction. And then in this particular case, our system had some leakage of air, so that we observed some nitrogen and oxygen leakage, unfortunately. But here, please focus our attention on these red curves. This is the hydrogen evolution activity. And as you see here, when we reached to X equal 0.2, we started to observe the hydrogen evolution. And then when we reached to X equal 0.33 or X equal 1/3, the hydrogen evolution activity becomes much better. However, when we increase more the dopant amount of magnesium, the activity will gradually decrease like this one. Then, as I said, this material, this analysis contains some leakage of the air. So after removal of air leakage, as you see here, both hydrogen and oxygen evolution is exactly in 2-to-1 ratio. So that and also that the absorption edge of these materials is still extended to about 680 nanometers. Actually, this is the first example of successful example of overall water splitting reaction on niobium-based photocatalyst and using up to 680 nanometers. So now let me summarize my talk. Niobium-based photocatalysts are attractive candidates for solar hydrogen production from water, and absorption edge of barium niobium oxynitride extended up to 760 nanometer, that is 1.6 eV, which is almost a theoretical limit, which can split water into hydrogen and oxygen. And preparation procedure of lanthanum niobium oxynitride significantly affects oxygen and hydrogen evolution activity. And as I showed in the last slide, that magnesium doping to lanthanum niobium oxynitride, lanthanum magnesium niobium oxynitride, has achieved overall water splitting reaction, which is the first example using niobium-based photocatalyst, closing to 700 nanometer absorption edge. And most of this work was actually supported by NEDO, that is the funding agency of METI. Thank you very much for your kind attention.